So this video lesson is going to focus on polarity of molecules and intermolecular forces. So things we've kind of mentioned and talked about with polarity of molecules, we're kind of bringing in intermolecular forces and then some of the lab things that we saw earlier this week. You should have the back of your periodic table and also your molecular geometry table that has like linear and bent and shows you all the geometries that we talked about before we get started. So first focusing on the polarity of molecules. We've talked a little about this. We're going to focus a lot more on it, what it really means for the molecules that kind of we're going to look at. So polar molecules have large electronegativity difference, causing electrons to spend their time on one side of the molecule more than the other. So for example, chlorine, if we look at our table, has electronegativity of 3, hydrogen's is 2.1, and looking at the table, that makes it a polar kind of molecule because the electronegativity difference is between 0.5 and 1.7. But regardless, because of that, most of the electrons are going to spend their time over here by the chlorine, because this arrow is kind of trying to show that most of the electrons are going to be over here at any given time because of the electronegativity of chlorine. It's a lot stronger. It's going to pull the electrons closer, so making the chlorine side partially negative, this side partially positive. That's where the polar comes from. But then we also have nonpolar molecules that have low or no electronegativity difference, and they have a kind of a symmetrical charge distribution here. Now, for example, we have the chlorines again. They have electronegativities of 3, carbons, which is 2.5. So again, each individual bond, so like if I look just at one of these bonds, is polar, but they're all kind of pulling equally on the carbon, all 4 of the bonds. They're pulling equally on the carbon, which makes their electrons aren't going to be in any given place more often than anywhere else. So that's why we can say this is nonpolar. Even though each individual bond is polar, the molecule itself, it's kind of balanced. It's kind of like a balanced tug of war. So all the chlorines are pulling equally on the carbon, which makes it nonpolar. Now, determining the polarity of a molecule or compound. This is all generally, and the key word is generally speaking. There are exceptions, but most of the things we're going to look at will follow these kind of rules here. So, what I would ask you to do, you might want to take your phone and take a picture of the take a picture of this page because we're going to talking about it a lot. And I say with your phone just because it'll be hard to find it in the video, and that way you can kind of look at it and answer the questions that you're going to answer. So molecules with linear, trigonal planar, and tetrahedral geometry will be nonpolar as long as and it's bolded, that's why it's bolded, as long as the atoms around the center atom are all the same. So like that example I just showed with carbon, it has all the chlorines around it. That's why, because it's nonpolar because of that, because they're all going to pull equally. If they aren't the same, the molecule will be polar, and there's going to be polar towards the more electronegative outer atom. So we'll kind of look at some examples here in a second about that, and we'll talk kind of more about those. And then molecules with trigonal pyramidal and bent will be polar because those electron pairs kind of push down on the outer atoms. It kind of creates a polar molecule, even though there might be the same atom on the outside. And we'll kind of look at some examples again. So, but these are your general rules. Again, I would take a picture of this with your phone or with something else so you kind of have it handy as you work on the questions that follow. And then go ahead and pause the video here and go answer questions 1 and 2 below. So you should have answered questions 1 and 2, and if you answered them, you should see that they're light up green by now. It should have refreshed. So if they're not green, go back and check and make sure you get the right answers kind of selected. But now we're going to kind of focus on determining the polarity of a molecule and compound. If I draw the Lewis structure, or if I'm looking at what I have What does the polarity look like? So geometry here. So we have carbon. It has four bonds attached to it. So it tells me that the geometry, and we're focusing on the molecular geometry. So there's four things attached to it. They're all bonds. So that makes this a tetrahedral geometry. Now, tetrahedral. Now, the thing we have to look at, and again, looking back at your rules, if you have that handy, if you took a picture and screenshot like I asked, we have to look at, are all of the compounds the same? So, or all, not the compounds, all the outer atoms the same? Are they pulling equally? And we can already see there's 3 hydrogens, but there's also a chlorine. So this is not going to be a polar molecule, or non-polar molecule. It's not going to be a non-polar molecule because these 4 outer atoms are not the same. So it's going to be polar. We know that, and specifically, and we don't necessarily need to worry about this too much. This chlorine end is going to be negative. The hydrogen end is going to be positive, because the electrons are going to spend more of their time here because it has the higher electronegativity, making that side more negative than the hydrogen side kind of the molecule down here. So again, the electrons, it's going to be polar regardless of where the positive and negative is. So tetrahedral, this is one of the examples where it's tetrahedral, but it's not polar for that reason there. So now looking at, let's say, boron fluoride, and that's not supposed to be showing down on the bottom, but you can clearly see what it's already going to be. But we have boron, trifluoride. Now, boron's an exception. There is no lone pair. So it's just 3 bonds attached to the boron. So again, 1, 2, and 3. It is one of those exceptions. It can disobey the octet rule. We don't focus too much on that. But so this is going to be trigonal planar, because it's just 3 bonds. That's it. 3 things attached. So trigonal planar. Now, since all 3 are attached, are all fluorine, they're going to pull equally on the boron, so which is going to make this a non-polar molecule. So we have a non-polar molecule here. That's trigonal planar. Now for the next example, so hydrogen, and one thing I'm going to draw on here. So the nitrogen trihydride. If we had the Lewis structure drawn kind of the way we would expect it, there would be a lone pair on the nitrogen. There would be 3 bonds and a lone pair. So a tetrahedral electron geometry, but that's actually really big. Trigonal, I'm going to abbreviate because I'm writing so big. Pyramidal. Oh, nope, I'm going to have to rewrite that. Okay. So trigonal pyramidal, let me make the text smaller. Trigonal pyramidal, I know that bothers some of you that the trig is bigger than the pyramidal, but I can't help it. So, trigonal pyramidal. So again, because we have 1, 2, 3 bonds and 1 lone pair, kind of forces all the hydrogens down here. So it's going to make this, because of that, and because it's trigonal pyramidal, a polar molecule. Because those hydrogens are kind of forced down below the nitrogen, and they kind of have to work up. Yeah, they're all the same, but it's not kind of... So this last example we're going to look at for polarity in geometry. So here we have carbon tetrachloride. So we're looking at carbon's our center atom with 1, 2, 3, 4 bonds, and that's it. That's going to make this a tetrahedral geometry, molecular geometry. And then the polarity, so this is going to be a non-polar compound. Now this looks similar to the first one we looked at. However, carbon is in the center with 1, 2, 3, 4 chlorines. They're all the same that are around it. So they're all kind of pulling equally on the electrons and the carbon itself, if you think of it as a tug of war. So therefore, we have a non-polar molecule. So go ahead and pause the video here and go answer questions 3 through 7. Make sure you have that screenshot of your notes handy if you need it, and your molecular geometry table. Now we're going to focus on intermolecular forces. So polarity is kind of half the battle. We have to be able to draw the Lewis structure, determine the geometry, to then determine the polarity. And once we've done that, we can talk about intermolecular forces. The root of the word inter, oops, that's what I wanted to do, but that's not what. Inter means between. So we're talking about forces or interactions between molecules. That's our focus here. So they're the forces between them. Intra, so if you look here, intramolecular forces are the bonds, the actual bonds between atoms in a molecule. So the bond between the hydrogen and the oxygens on water. And then our intermolecular forces are forces or interactions between different water molecules. I'm kind of looking at an example, some images. So we're talking intramolecular forces. We are talking about these here. So a bond, and not necessarily a bond, but an interaction, a force between the negative side of an oxygen, a water molecule. So here, the negative side's attracted to this positive side, or the hydrogen sides of the molecule. And then here we said, like, there's our bonds. So a bond between the oxygen and the hydrogen in water is stronger than this over here, but this is what gives water its special characteristics. These strong interactions, these strong positive and negative, the polarity of the hydrogen in the waters, the hydrogen and the oxygens in the water is what we're focused on. So these interactions, and I'll kind of circle them, these would all be kind of our interactions between the individual water molecules that make water so strong. Why it has a high boiling point. It takes a long time to evaporate because of those strong interactions between each individual water molecule. So, and then down here, if we looked again, so here, the hydrogen side of hydrogen chloride is much more positive than the chlorine side, so it forces an interaction between the two. Again, it's not as strong as the actual bond between hydrogen and chlorine, but it's still an interaction that we can talk about and look at. And just noticing those things, the ones that we can talk about and focus on. So van der Waals forces or London dispersion forces, those are the interactions between nonpolar molecules and noble gases. They just result from, so nonpolar don't really have a net charge. However, the electrons are always moving around, so which tells us, like, at any one time there could be more electrons on one side of the atom compared to the other, which will make that part of the atom or that molecule slightly positive or slightly negative. So any nonpolar molecule will always be have London dispersion forces between each individual molecule. Then we can talk about dipole interactions here. So those are interactions between polar molecules. They result from differences in electronegativities in the overall dipole partial charge. So again, we talked about this. Hydrogen side is always kind of a little more positive than the chlorine side. So interactions between so more than one hydrogen and chlorine, we have those interactions between the two. And then we also have a special type of dipole-dipole bonding, which would be hydrogen bonding. So hydrogen bonding is a special type of dipole-dipole interaction, but it's only when we have bonding of hydrogen to fluorine, nitrogen, and oxygen. So only then. So just because there's a hydrogen, so for example here, hydrogen chloride, just because there's a hydrogen does not mean I have hydrogen bonding. It has to be bonded to an oxygen, a hydrogen, or a nitrogen. If it's not, we don't have hydrogen bonding. That's the biggest thing that we have to, because the mistake you'll make is that we'll see hydrogen like, oh, hydrogen bonding, I'm done. Nope, we have to focus on, it has to be attached to a fluorine, a nitrogen, or an oxygen for it to be hydrogen bonding. And just to discuss the relative strength of those intermolecular forces, when we talk about them, the van der Waals and London dispersion forces are the weakest, just because they only result from just that imbalance. So that partial charge isn't going to be that strong. Dipole are then the next strongest, followed by hydrogen bonding. It's the strongest of the intermolecular forces. So we kind of draw a line right there, because we have, these are our intermolecular forces, so the ones between molecules. And this would be our intramolecular forces here. So we could look at inter and intra there. So ionic and the bonds between individual atoms, so the carbons and the chlorines, or the hydrogens and the chlorines, those are stronger than the interactions between the molecules. But we still talk about the intermolecular forces for that. So hydrogen bonding is our strongest intermolecular force. Van der Waal, so hydrogen bonding, Van der Waal forces are the weakest of the intermolecular forces. So go ahead and pause the video and answer questions 8 and 9. So kind of looking at our examples before. So these are the same examples. So we said that this was tetrahedral. I'm going to kind of shorthand some of this. So tetrahedral. And we said this was polar because we had a kind of the negative side here and the positive side. That was the example. These would be the same examples just to save some time. Now, it's polar, so that means I can either have dipole or hydrogen bonding. Now, here's where you have to pay attention. Yes, we have hydrogens here, but they are not bonded to an oxygen, a nitrogen, or a fluorine. So the only IMF we can have between, if we had more than one CH3Cl, would be dipole. So we have two options, which was dipole, and hydrogen bonding. We can get rid of hydrogen bonding because the hydrogens, yes, there's hydrogen, but they're not bonded to a nitrogen, oxygen, or a fluorine. So, and again, we talked about boron. It doesn't have any lone pairs. It's kind of an exception to the octet rule. So, but it's trigonal planar. It was non-polar because the fluorines are all pulling equally on the boron. So since it's non-polar, the only thing it can be is London dispersion forces. And you'll hear me use the term LDF to shorthand it. So LDFs are London dispersion forces because it's non-polar. Non-polar, the only type of IMFs it can have are London dispersion forces. So, looking at nitrogen, again, we said that, again, there's let's make that a little bigger. There's really a lone pair here on the nitrogen. So we said that it was trigonal, pyramidal. So it's trigonal pyramidal, which made it a polar molecule. Now here, polar, again, it has to either be dipole or London dispersion. And in this case, sorry, not London dispersion, let me walk that back. It's either dipole or hydrogen bonding. And in this case, it's going to be hydrogen bonding because these three hydrogens, remember our rule, are bound to a nitrogen. They should be bound to a nitrogen, an oxygen, or a fluorine. So since they're bound to nitrogen, we have hydrogen bonding, which is, again, one of our strongest IMFs. The strongest IMF is our IMF here. And the last example that we looked at, we have a tetrahedral. And remember, this was non-polar because all four outer atoms are the same, so they're pulling equally on the carbon. So this is, I'm going to shorthand LDFs. So it's an LDF. London dispersion forces because it's a non-polar molecule. Non-polar all molecules can only be London dispersion forces. So go ahead and pause the video and answer the last three questions, number 10, 11, and 12. and you'll be done with the video lesson. And again, remember, all of your questions should be lighting up green as you answer them. So if they're not, go back and fix any questions you didn't answer.